I don't think I said this properly. There's two types of sets. Or I should say, yeah, types of sets. One is disjoint and the other is independent. Y'all remember these terms? Now, I'm going to try to make sure you understand something. Disjoint just means the members of one set aren't part of the other set. So if you talk about disjoint, and you have, and I'm going to use a Venn for this, A, and here's B. No, there can't be an edge shared. That's what it amounts to. There can't be anything in one that's in the other. That's all it means for disjoint. And if you look at this, simply the A intersect B, they use this symbol. It's zero. There's nothing. It's called a null set. Nothing in there. Y'all follow? It's just the fundamental definition. Now, when you talk about independent sets, you can have literally that same Venn diagram. I'm just making this point. I mean, this is not really that big of a deal, but if you look at this guy, his writing style, it's mathematics. The guy is coming from a strict math background. He's being very clear about corollaries, axioms, and everything like that. I'm an applied engineer. Everything I do, really, the time I have to be very exact is if it deals with an outcome that I want. For instance, identifying a target or not. But a lot of stuff is not really important. So, independent sense, if you have A and B, well, matter of fact, let me do it this way, then I'll tell you what independent is. I'm going to do it this way on purpose. I'm going to say B's right here. Now, I'm showing you an area of overlap. Everybody with me? Now, when we take a look at A, and we talk about A and union B, that's this entire area here. Now, this is just kind of a Venn diagram representing it. It's everything, right? But it never has that area where both exist twice, just once. Do y'all follow me? Now, here's where the independent set thing comes in. If you talk about the probability of A given B, by the way, do you remember the name of this theorem I'm about to put up? Some of you do probably. Begins with a B. Second letter A, Bayes' theorem. Y'all remember what you're talking about? Bayes' theorem. So if I look at this, I know, let me make sure, let me make this clear. That's the overlap area, A intersect B. Now when we take a look at the probability of A given B, that's equal to probability of, if you look at this, well, let me get to it. It says B occurred, so B happened. Now think of ratio of areas. If B happened, try it this way. So this happened. I always think about this in ratio of areas. That happened. What is the probability of this happening? And it's an area. The area where they both exist versus the area of B. Y'all with me? The overall omega has nothing to do, it doesn't matter how many different things are there. If we say one thing that has occurred, immediately you might say the space we're interested in is cut down to just that size. Now the probability that this occurs is just an area ratio. So it's really going to be the intersection of A and B, or the probability. Now I'm using probabilities, I'm not just showing you something with, that's basically very abstract and vague. You with me in this class? So it's going to be a probability of A intersect B over the probability of B. And I'm going to say one other thing. Because this A intersect B is important to understand. Everybody knows what that means, right, class? We're talking about a kind of an area ratio to get the probabilities. And this just helps you in your mind think about it. But I also know that the probability of B given A, I went through this, but I'm making a point for a reason. If you look at this, the probability of B given A, maybe I better do it right here. So here's A, and here's B. And now I say A occurred, let's say you put them up. This occurred, I want to know the probability of this sliver right here occurring. That's the same idea, y'all follow me? The overlap there is the same, but now, if I say A occurred, probability of B, it's still gonna have the P of A, and it's intersect B, same thing's common to both, over P of A, or the probability of A. And its ratios varies again. It's the best way I can think of explaining it. Actually, it's n-dimensional space, if you really want to be true about this. It doesn't have to have just 3 dimensions, it can have n different orthogonal dimensions, which is a little hard to grasp. But in an exact mathematical way, he'd state this with a lot of summations, and it would have a whole lot of things going to infinity. But the essence is area. Follow me, everybody? Okay, now what I did last time is I said, therefore, and this is based on the way he likes to write in the book, of P, A given B, is equal to, and here I'm going to say, well, this times P of B here is equal to P of A times the probability of B given A. The only thing I'm doing is rewriting it, but I'm trying to do it from the starting point being just visually seeing this. That's basic, and here's what people can do, and it's not wise to do this. They're gonna memorize certain things. And then all of a sudden, I'm not gonna use A and B, I'm gonna use C and F, or something like that. And then they're gonna get terribly confused. So try to make sure you understand the area representation of this. And a few other things. I didn't complete this one, but I want you to listen to me. The next thing I want to do is extend this. I didn't complete it last time. What if we have 3 sets? One other thing too, I didn't say this. If we take a look at this right here, A and B, these are both disjoint and they're independent. One does, if one occurs, the other has. We don't know if it occurred or not. You all follow me? If this occurs, you don't know if this occurred or not. In other words, it's independent. You all follow me in that class? It means that, let me give you an example. Suppose I have a die, and I say my first outcome is the value on the die surface, basically 1 through 6. Follow me? Then I have another thing, and it can be red or blue. So what's the probability of the die having a 3 given that a blue was the second outcome? The blue has nothing to do with it. Y'all follow me? It's just the first. Y'all with me on this class? That's independent, and the easiest way to understand is something like that. So if you take a look at this, well, the probability of A occurring is just probability of A. Again, think about the die. Suppose I have 1 through 6 as the possible outcomes on the die surface, right? I roll 1 die, and the first thing is just the probability of a 1 or something like that, probability. I want to know how that relates to this. If this is blue, red, white, and blue, okay? There's no relationship. Y'all follow me? So when I take a look at the probability of A given B, that is just probability of A. Does that make sense to you? If it's independent. How many understand it? It's the easiest way I can explain this. Did anybody read the book on this in chapter 2 where he goes through this? You did? He spends some time discussing this, but the essence, I didn't see it just jumping off the page at me, the way he does. Disjoint, he doesn't really contrast disjoint, which just means none of the members are together. Let me give you another example of disjoint, and I'll get to where I'm going with that in a second. But here's the best example of a disjoint set. I toss a coin 1 time. If it's a zero or a tail, all right, a tail, it's set A. If it's a head, it's set B. What is the probability of A intersect B? 0, can't happen. Y'all follow me? It's forbidden. That would be the best example of disjoint. Disallowed, think of it that way. One cannot occur if the other does and vice versa. Now, I'm going to tell you there's a lot of these mathematical definitions where he uses something where he'll have vertices, and he'll say disjoint means no two vertices or edges can be shared. He doesn't use that kind of curve type of drawing to indicate A and B. They're straight lines. Yeah, that's true, but it doesn't really help you really get a grasp of this, and I hope what I'm doing is helping. I mean, Bashir, I don't know why he chose this book. He's a very bright guy from MIT, but it's almost like too much time on very exact mathematics without applications to see what it really means. So I'm telling you that. Now, if that's the case, it's probably, if it is, I should say this is independent. If it's independent, then the probability of A given B is just probability A. Getting back to this thing, when it says the probability if it's independent, the probability of A given B, and I'll do it this way, is probability of A intersect B over probability of B. Well, it's just saying the probability of A intersect B. Now just think about it. If it's independent, probability of A given B is just probability A. Y'all with me? This is my point. Well, that's just going to be probability of A times probability of B. And that is if they are independent. A lot of this, you almost have to see it applied to specifics. But that's what independence means, and we'll use that a great deal. And you'll see the benefit later, too. This joint, I don't even think about all the stuff I've done with radar and others. I don't remember ever using that in particular. I'm being honest with you.
Is there a numerical example you can do with this?
Yeah, we're going to do it. Let me just finish one thing and we'll do an example.
I figured you would.
I've got great examples. Sorry. I'll get to the three sets, but first I need to talk about this. I want to just finish this thought. I have ideas about the way I want to talk about this, but I first want, before I go any further into the lecture material, I want to make sure I underscore all this, because I think on that last quiz there were a few people that didn't quite understand some of these, and that's one of the reasons I'm doing it. You got the grades are great overall, but I'm just making sure there's no uncertainty. Okay, now what about this? And we think about this, I did it last time. Here's A, last class. B, here's intersect there. A, right? Intersect B is right here. This is just showing you a Venn diagram, nothing with probability. Now the probability, and I did this one, but matter of fact, let me ask you this. What is the probability now, of A, all right, union B, not intersect? I'm not going to ask you to answer this if you don't want to. How many remember me talking about this? No? Elijah? No? Okay, you do. How did I do that? You remember what?
It's the probability of A plus the probability of B minus.
You're just reading it though. It's not.
I wrote it. Yeah.
Let me just, I'm trying to make another point here. So if all possible outcomes are omega, he loves that. It's alpha and omega. Omega is the last Greek letter, so it means everything. Then if that's all possible outcomes or whatever we're talking about, and we look at this, A intersect B or A union B, that's this area, you might say, the probability associated with that area over omega, correct? Now what does that mean? You're right. I'm glad you can read well. It's going to be the probability of A. That's just this area, but then think about the ratios. Plus the probability of B. All right, now here's what I've really done. The probability would have to do like A over omega, whatever that areal ratio would be. Y'all follow me? He doesn't specifically say that in the book. But you see, I've counted this area twice. Can everybody see that? How many can you see it? So you have to subtract one of those probability of A intersect. So now I subtract probability of A intersect B, and I did that last time. You'll see problems like this coming up, but it's important to get a handle on what I'm talking about, right? Everybody with me? Did anybody look at the examples of his where he said, you roll a four-sided die, basically you got numbers 1 through 4 is probable coming out, right? And he says, let outcome X be the roll of the first dice, and it basically is going to roll it twice, outcome Y be the roll of the second dice. And then he defines an event, which is a little irritating, because he's complicating it unnecessarily. So he says, I don't even know what he called it, but I'm going to call it like, let E be the minimum of X comma Y equal to, do you remember this one? Anybody in here? It's a great example, but it's complicated. All right, so if you roll the first dice, you get a 2, roll the second dice, get a 2, right? The minimum's 2. If you roll the first dice, get a 1, second dice, get a 2. Still, the minimum of those 2 is 2, right? And you look at all the possibilities for the minimum being 2. Out of the possibilities, there's 36 possible if you roll a dice twice, right, for the numbers. Okay? Then he says, I'll call it, if that's F, I'll call this H. Event H is going to be the maximum, I think it was 3. Y'all with me? So he wants to know if F and H are independent or not. Now, you can see this gets a little more complicated than necessary to make the point. Y'all follow me on this? Anybody read this one? Oh gosh, I need to tell you where it is because you need to underscore this. This is the way the guy thinks. He doesn't make it simple. He's going to make sure you're going to stretch you're going to push yourself every time I give you something to think about. That way, you'll be ready for anything. It's my opinion of it. I've had books like this before when I was an undergrad. In graduate school, sure, then they make it terribly complicated, but not undergrad. Not with the basic points. So let me tell you what this is. And I'll get back to that in 1 second. I got it. This is chapter 2. Dog-eared this page. So if you look on page 83 and 84, not really, by the way. Yeah, four-sided die, which always bothers me. Stick with 6. But here we have 4 possible outcomes. X be the first roll, Y be the second, let B be the event, B, the minimum of X, Y is 2, and then M be the event, the maximum of X, Y is 3. Boy, right off the bat, he kind of makes you stretch. And then he says, find the probability of M given B. All right? You gotta have to think about this one. He shows you how to do it, and I'll get to that in a second. But that said, that's the level of complexity he likes to use as examples. He's not somebody that makes it easy. And I'm going to give you specific examples that I consider more obvious in a second. But first, getting back to this, because I have to tie what I'm about to do into this, so you'll see some of the things that he talks about that'll drive you a little nuts. Now, if you look at this, right here, if they were independent, listen, if they were independent, then this becomes probability of A times probability of B, right? Write that down. So if they're independent, this term becomes minus probability of A, probability of B. And what I'll say is, right here, this is only true if independent. And keep that in mind where I'm about to go with this. I'm gonna come back to specific examples, don't worry. But now I wanna extend this, and I wanna do it right here because I've got your attention about this. And I'll ask everybody. Matter of fact, I didn't complete this, but I'm going to. So now, here's the Venn that gives you an image to think about. I'm gonna say A is here, B is here, and C is here. Okay? Y'all with me? Now, after that's said, I can see A and B have an overlap here. And I can see C and A having this overlap. Can y'all see this? And I can see C and B having this overlap. I'm trying to show you multiple colors. Right? And again, this is A intersect B, right here. This is A intersect C. And this one is A intersect, B intersect C. Okay. Now, try to do this, just reason with yourself. I want to know how to get the probability of A union B union C. Y'all with me on this? Think of the, extend the one I did previously. I did not go through this. I kind of wish I would have on Friday. All right, how do you do it? Well, almost always you're going to start with the probability of each one separately. That's a given. You all make, no matter how many, it could be C, D, E, F, G, you're going to start with them all individually. So, probability of A plus probability of B, and this is area, think area. Getting all the areas possible, plus probability of C. Now I've got all these areas, right? What do I need to do now? Well, ideally, what I would do is I would simply take all this and remove it, right? The area associated with that. But that's a little tough to do in one statement. So how about if I do this? Now just listen. Suppose I remove this area first. That's going to be the probability of A intersect B. With me? Just as before. Then, bless you, I'm going to remove this area, the probability of B intersect C, and then I remove this area, the probability of A intersect C. Everybody with me? Well, that's getting there, but what happened? Now I need to add this area of overlap back in 3 times. Does that make sense to everybody? How many see this? You see it back there? With me? So what would that be? Got those things. Now I'm going to subtract P A intersect B minus P B intersect C minus the probability of C intersect A. By the way, these operations, order doesn't matter. You can have probability of A intersect B or probability of B intersect A. Some of this is pretty obvious. They have definitions for community properties and things like that. But this, I don't spend a lot of time. Is everybody clear on that? And now what do I need to add back? Yeah.
3 times the union of all 3?
Plus, that's right. Probability, it's not union, intersection.
Intersection.
Of A intersect B intersect C. And yes, in fact, you get it. Now you understand the rationale, right? Here's one for you to try. What would happen if I had D? Well, I'm going to start A, B, C, D, right? Got that. Then what am I going to do?
Subtract all like the one-off intersections?
All the intersections that are just between A, B, B, C, C, D, and really A, D. Y'all with me on that? But then that overlap area, things happen. Now, what do I have to do? Now I've got overlap areas between A, B, and C, but not D. B, C, and D, but not A. Y'all follow me? So now you're gonna have to, this gets a little maddening. You gotta play with this until you can actually get the areas right for the probabilities. How many understand that thought? Now you're probably wondering, would you really ask us this? If I was gonna ask it, I'd give you several problems that deal specifically with it. All right, and the reason is they're time consuming. Now you asked, did you ask for a specific example or did you? Here's some examples. And the reason I do this is, and these are in the book, and I got a lot of, I'll go back to that one in a second. Okay. Erase this. Is this making sense to you? I'm trying not to spend too much time on mathematical definitions of some of these things, like a line that goes from 0 to 1, where it includes 0 and 1, versus a line that goes from 0 to 1 and excludes the points. And those are just simply brackets versus actually curly bracket, or really parentheses. There's a lot of these things that he's big on, but don't really help you solve real problems. Okay, next thing. So for this problem, I'm going to post some of these things for you to do, because the more problems you do, as you do them, and I'll give you the answers, you'll develop confidence. A lot of times there's uncertainty, and that will kill you in this class. I really mean that. As we get further along, this particular class, I think I mentioned this, in my opinion, is the most difficult conceptual class you take as an undergrad. Signals and systems is a little abstract with Fourier, Laplace, all that. But this, especially when it gets complicated, is really crazy. I really think the only way to feel good about it and know it is to do a whole lot of problems. That's my own opinion. So for this one, I'm going to say probability of A is 0.3, and probability of B equals 0.4. I'm going to say something now, they're independent. I could draw the Venn, but you know that that just means A and B don't have any overlapping area. So I'm going to say these are independent. Assume that, all right. Now if they're independent, let's see, what does he want? And this would be a question I would ask. I would feel very comfortable asking this. If I wanted just the probability of A given B. Now think about it, especially if you spend a weekend not thinking about it. Well, remember Bayes' theorem. And remember, do y'all remember this? Please remember. If you look at this, here's A, and here's B, right? And I said probability of, these happen. So probability of A given B equals, do you remember this class? What do I put on top? Now I say B occurred, yeah, you're right, but hang on. So I'm saying this happened, that purple. So if it happened, and I want to know the probability of A, it's this sliver of area over the total area of B is the way to think about it. Make sense? So what do I put here? Whoever said it. That's right. Probability of A, right? Intersect B over
Probability
right. And then the word independent comes in. So if they're independent, the probability of A intersect B is equal to the probability of A times the probability of B. I put that down earlier. Do you remember that class? Everybody with me? This is important because people say, well, how do I get this? I don't have a Venn diagram. And he just told me the probabilities, but I said they're independent. Independent does one thing for you. It lets you replace this. Since they're independent, it means the probability, I put it down there, right? Or no, I did, but I took it back. Probability of A intersect B is just probability of A times probability of B. Follow me on this, class? Everybody with me? So, come over here, and what you would write is, that would be probability of A intersect B over probability of B, but you know, now that they're independent, I can say the probability of A intersect B is just equal to P of A times P of B, right? So the first thing I think he asked, or this is from a different book, is probability of A intersect B. He asked this. So that's going to be what, class? Just, can you all read what I wrote? What is it? 0. You're right, 4 times 0.3 or 0.12. With me? I want to keep going on this one because I can see the possibility of mistakes being made if you're not aware of what you're doing. Okay, now what's the probability? I think of a lot of them. Probability of A union B. Do you remember how to do that? Remember how we did it before? How many do? I'm not going to ask you to. You remember me talking about this? What did I always say? Come over here. I want A union B. That's all that area. The probability of that into that omega region, right? Do you remember what it is? The probability of A union B is equal to
P of A plus P of B minus P of A intersect B.
I think you're reading too, but that's okay, right? But what do we have to do? Subtract the intercept, right? A, and it's going to be intersect B. Okay, that's the first part that I wanted to get down. Does everybody follow me on this? So there's one part. Remember, they're independent. So what do I change on that?
It's P of A times P of B.
Yeah. What I'm saying is this intersect here becomes just P of A times P of B. You all with me? Please make sure you see this. So this becomes P of A plus P of B minus the probability of A times probability of B. And the only reason I can do that is they're independent. Now, I'm not using numbers per se for A and B. We can put those in later, but the complexity is unnecessary. You got to just see this if they're independent. You with me? Can you see it? You good with that? Okay. What's that going to be? Well, that's 0.4 plus 0.3 minus PA minus PB is 0.12. I think that's 0.58. Is that right? All right. You can see I can extend this. I'll tell you one other thing. So think about, I'm not going to do this right now. Remember how I had 3 sets? So if I say if I got 3 sets, probability of A is 0.4, probability of B 0.3, probability of C 0.2. Suppose I say they're all independent and I start asking for things. You all follow me how you extend this. It should be logical. You with me on this, class? But if I say A and B are independent, but A and C are dependent, and then I give you the probability of A intersect C, and it's different, just times A, probability of A times probability of C. You should be able to work something like that, a logical extension of what I've showed you. Do y'all follow me? Elijah, you're looking at me like I don't like that. I just got to make sure you appreciate the type of thing I'm expecting you to do. Take a logical extension in the complexity. I'm not going to ask you to do something insane, but that's the kind of thing. With me? I'll get to that problem I mentioned about min and max, which clearly takes the crap out of me. because the way he does this, he throws that at you first thing, and it's like, that's really asking these kids a lot. Wait a second. This class is over at 11, right? Oh, anytime I see people looking at their watch, I've done it again. Okay. One more on this. You asked for it, so I'm gonna do it. I have some more complicated problems, but I don't want to spend too much time, unless it's really necessary on some of the complicated ones. His problem will do. I'll ask you specifically about this. So for this one, okay, we're gonna have two boxes. This is actually a problem 450 from another. I think it's from Shams out. It is Shams out. It says 5 red marbles. So this is box A. It has 5 red marbles, 3 blue marbles. And box B has 2 red and 3 blue. It doesn't matter what they are. Think about marbles. It's easy. All right? Now he wants some stuff. First, he wants to know what is the probability of 2 reds. Red in the first box, red in the second box. This would be number 1, or so A, and this would be B box right here. With me? So what would that be? First, let me ask you, do you agree A and B are independent? I mean, I'm trying to make that point. We're not talking about shared box. This is 2 independent. All right, so what's the probability of a red and a red from box A and box B? Look at just the first problem, or the first box. Just knowing this, what is the probability of getting a red? It's ratios.
Probably.
Total is 8, right? There's 5 red, so that probability would be 5/8. Do you agree with that, everyone? First. Extend that to the next box, not you, somebody else. How about the back? What's the probability of getting a red one from box B? Can you read it? I got 2 red, 3 blue, total.
It'd be 2/5.
Yeah, total is 5, 2/5, right? Agree? Or 1.4. So that would be 2/5. Now, you told me they're independent. They are. So that would be the problem. Do you agree with this? What is that? Well, the 5s cancel, and I would have 1/4. Do you agree with that? All right. Now here's the one you pay attention to, so you don't go nuts. What's the probability of at least one being a red and the other one being a blue? So probability of red, blue, plus the probability of blue, red. Basically, the probability of having 1 blue and 1 red, regardless of order. With me? Now you can go through every single permutation of what can happen. Grab one from one, one from the other. But there's this, I'm trying to show you, this is an easier way. He tried to lead you into it, the first one. First, what is the probability of having 1 blue, 1 red, plus the probability of having both red, plus the probability of having both blue? What would that equal necessarily? 1. That's every possible outcome. That's omega. Follow me? It has to be 1. That's the only thing that can happen. You can't have no marbles if you were defining an outcome as grabbing a marble out of A and then grabbing a marble out of B. Okay, well, it's 1. So if I want the probability of a blue and a red, yeah, we can make it complicated, but how about if I just say that would be 1 minus the probability of a red, red, minus the probability of a blue, because now whatever's left is what? It's gotta be a blue and a red, right? I'm showing you this. You can do it the other way if you want. You can say the probability of blue first, red second, plus the probability of red first, blue second. You get the same answer, but I'm trying to show you this is a good way to think about these things. If you're looking for something where there's a lot of possible permutations, always look, if you took the entirety, the one, all possible outcomes, that probability, and subtract it from some of the smaller ones, would you be left with the actual probability you want? And in fact, you are. Do you all agree with that? All right, what's this gonna be now? Well, it's 1 minus the probability of red is 1/4. You agree with that, class? And what's the probability of blue? I think you guys got this. And I don't mean to irritate you doing this over and over. Well, what's the probability of getting a blue in the first one? Just
3/8.
3/8, right? And they're independent, so what's the probability of getting a blue in the second one?
3/5.
3/5. Now, if you look at this, I see I got 40. I said this is what? 1 minus, or basically, yeah, 1 minus 1/4 minus 9/40. I'm just writing this down. And let's see, that's, if I take 40 here, I can say 40 here, then I have 40 here, because I'm getting a common denominator. Then I'm minus 10, right? And then minus 9, and that's 21/40. Do you agree with that, class? I'm just doing the math. And that's true. That's the way you think about these problems, and those are specific examples of independent and how you calculate these things. And we can always add complexity. I can make another set and say either independent or one of them is not independent. And you can extend this, and I'll give you problems with all these type of permutations. But that's pretty good as far as, and that's a simple example. One he does in a book, and admittedly, I suppose to him it's obvious. But before I do this one, I'd like you to all, for homework, do example 2.46. Here's what he's really asking. And I'm going to try to tell you why it's concerning me. Because I can see how this can confuse you to no end on the quiz. I'm thinking about what can happen and go wrong a lot. So just listen. First he says, consider a tetrahedral four-sided die. It doesn't exist. I mean, yeah, there are ways to do it, but normal die are 6 sides. So it's really say something where the outcome is 1 to 4, discrete. With me? That continues. Let X be the first roll and Y be the second. Now he defines an event B. This is an event space. He says event B is the minimum of X comma Y. Either is 2. Then he says, and let event M be that the maximum of X comma Y is 3. Okay. Now he wants to know something. Are they independent or not? Y'all with me? I mean, y'all follow me on this. I'm going to show you this. This is why. This problem itself, if I gave on a quiz before you went through the kind of ration, you'd probably have some trouble. So I didn't even get into this, but I said if they're independent, then there was something that happened fundamentally if they were independent, and it was that if you talk about independence, the probability of A intersect B is just equal to probability of A times probability of B, right? That would be true if they were independent. If the probability of A intersect B was unequal to that, They are not independent. I didn't say that explicitly. Y'all with me? So if you can show that is true, then they in fact are independent. If it is not true, they are not independent. That's what he means by asking. So if you look at this, we got 2 die, and we have x, right, as the first outcome. X could be 1, 2, 3, 4. Agree with that? Matter of fact, let me, because I want to show you the way, he does it a different way to think about it. If this is x, you're going to have 1, 2, 3, 4, oh, just 4, that guy. Then 1, 2, 3, 4, you'll see why I'm doing this. 1, 2, 3, 4, 1, 2, 3, 4. Now remember, we're going to roll the dice twice, right? So there should be 16 total outcomes. We could have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, I mean 1, 4, then 2, 1, 2, 3. You follow me on this? That's the reason I did this. I'm going to show you all possible outcomes. Then for y, you get 1, 2, 3, 4. Actually, why don't I do this? I should do it this way. I should have 1, 1, 1, 2, 1, 3, 1, 4. I'm sorry about 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, and finally 4, 1, 4, 2, 4, 3, 4, 4. I'm doing it this way. He does it with it, and he shows us where he has outcomes in the first one on top horizontally, I believe, or I'm sorry, vertically down with x, 1, 2, 3, 4, and then outcomes of the second one, 1, 2, 3, 4, going horizontal, and he's going to show you. All right, if you look at this, the first event x is defined as the minimum of x, or I'm sorry, he calls this, I think he calls it b. This is event b. The minimum of x comma y is 2, and I better be sure about that. And m be the event xy, the maximum of xy is 3. This is event b, and this is event m. And then that is the maximum of x, y equals 3. Now, what I'm going to do is kind of the brute force way of showing you how to do it, but it's a little more obvious. If I look at this, I need to find out which ones have a minimum of 2. That means either of these has to have 2 as a minimum. It can be larger than 2, but the minimum is 2. In other words, it discounts anything where you got 1, 1. Y'all with me? Minimum of 2. Well, here's one. Y'all with me? That's got a minimum of 2. Where else? This one, 2, right? This one, minimum of 2. That one has a minimum of 3. That one has a minimum of 4, right? This one right here has a minimum of 1. You all follow me the rationale. This one right here works. And what else? That's 3, 2, 3, 3 doesn't work. 4, 2 does. Or I'm sorry, it's 4, 1. 4, 2 here does. Right? There's 16 total numbers. Can everybody follow me on the reason? How many understand? Are you with me on this? Can you see it? Over here? I mean, I'm really making an effort to show you this. When it says minimum, it means you can't have a 1. If that makes sense, right? And you can't have you gotta have something with at least a 2 in it, and you all with me on this? Minimum of 2. That's what it means. Yeah.
So why isn't the 2, 3, and 2, 4?
Actually, didn't I put that down here? Sorry. You're absolutely right. That's it, and that's it. They have a minimum of 2.
So the 1, 2, and the 2, 1 would go away?
No, the 1, 2 had one. You're right, that's not there too.
The 2-1.
Now, also goes away. Those are not intentional mistakes, I'm just tired, having allergies, but. So I got that one, that one, that one. I think we're good here. All right, so for event B, I got the probability of B being the total number. Thank you very much. So I got 1, 2, 3, 4, 5 out of 16, right? What about the probability of A? The maximum of xy equals 3. Let's see if I can do this right, or maybe you can help me. I want the maximum of x or y being 3, right? Maximum. Well, that one, right, doesn't work. 1, 1, right? What do we need in there? A 3, right? And we can't have a 4, right? So we need a 3, but we can't have a 4. This one does it. A 3 but can't have a 4. That one does it. A 3 but can't have a 4. That one does it. 3 but not a 4. This is 3, 3. That does it. That doesn't do it because we got a 4. Does that look right? So what's the probability of A? It's going to be what? 1, 2, 3, 4, 5. Unless I'm 5/16, right? Now, what is the probability of a minimum of 2? Now listen to me on this one. This will get you. The first thing, is it has to have a minimum of 2 and a maximum of 3. As a matter of fact, let me just check, because I'm trying to get. Well, actually, he says find the probability of M given B. Just get this. So he wants to see the probability of M. That's the second event given B, the first event. So it says the first event happened. Do y'all follow me on this class? What's the probability of the second? Think about areas here. So the first event is a minimum of 2. I call it A. This is probability of M. I'm so sorry. He's using M for the second one. Okay. And now he says he wants the probability of M, maximum of 3, or B, given M. So really, what he's saying is probability of 3. Look at this. Let me just see if I can do this from the areas. This should be it. So B occurred. All these are possible. And this one. And the probability that M occurs. So I got 1, 2, 3, 4, 5. And the overlap So I got, this is 2/5 right here. And if they're independent, right here, this should be probability of B intersect M over probability of B. So the probability of B is 5/16. And the intersection of B that's going to be a B given A. If you look at this, here's where I'm going with this. So I'm trying to find the intersection. I'm looking for a purple and a red check. That's 1, 2. So this is going to be 2/16, right? So that's 2/5. And in fact, that's 2/5. Y'all follow me? I'm spending a lot of time on this. I'm sorry. I'm feeling a little, I don't mean to, but now what do you see with that? In fact, they agree, right? Therefore, they are independent. If you go through it another way, he does it in the book, but the real reasoning is, whenever they're using maximums and minimums, you don't usually use that, I don't think. Maybe in MATLAB you do for your programming, but you're not used to thinking that way about outcomes of events, n events, where the maximum possible would be like a 2 or 3 or something like that. But this is something, please go through this one and think through it. I think it'll be clear to you. I'm sorry, I'm doing it this way. He does it where he has, I did it that way for a reason, because I think it was a little more obvious to me. What he did was this. He has 1, 2, 3, 4, and then he has 1, 2, 3, 4. So he talks about the first one, the first event. He'll show it to you as a execute first one. So it's got a minimum of 2, and what he'll do is shade the area for, and if I call this X and this Y, so event B is a minimum X and Y equals 2, and he'll go ahead and what is that going to be? He'll come over and shadow this right here, and then he'll go for the second one, a maximum of 3, and what he'll do is look at the overlapping areas. Y'all follow me on this class? It's a little hard to see there, but please take a look at it. I want to cover two or two other things, and I've spent a lot of time with that one, but I think it's worthwhile. All right, now, after that's said, he's going to talk about, he'll show a couple more things with more complicated stuff. I'll give you some more problems, but here's the thing. Now when we get into discrete random variables, we're going to talk about something called a probability mass function, and then a probability density function for continuous stuff. This stuff will make a little more sense, and this is stuff I work with all the time. It'll be less ambiguous with just letters and single numbers and integers. I think you'll understand this part. Okay, so I'm going to give you an example, and I'll show you when they talk about a probability mass distribution. I think he uses that term, but this is in chapter 3. He likes probability mass function, that's fine. Usually I term it probability density function, but this is for discrete variables. And let me give you an example. Suppose I have a die, so I'm going to have a die, a single die. Possible outcomes are 1 through 6, right? Now, if you take a look at something, and on this axis, the vertical axis, write this down. I want to make sure you see this. On this axis, I'm gonna show you what's called the probability mass function. And he calls it probability mass function. Don't worry about the terminology. You're gonna see it's just the probability of an event occurring. Now I'm gonna show you on this axis the possible outcomes. So this is gonna be the dice value or die value. Well, I can't have a 0. Do you agree with that? No, I don't have a 0. They have 1, right? It's the lowest possible. So I'm gonna have 1, 2, 3, 4, 5, and 6. Those are all possible values of the outcome of rolling a single dice. Now he's trying to illustrate this so you'll see what's going on. The probability of each one of those, if it's a fair die, has to be 1/6. Do you agree with that, first of all? Now it doesn't have to be, but it should be. Otherwise it's called a loaded die. There's 6 possible outcomes. That type of a drawing where you see the probability, mass function, or density, the likelihood of each event. Here's the events possible. There's the likelihood. That thing is called the probability mass distribution. Now some things, if you look at this, will be very obvious. What is the probability? What if you summed up all those values? So this is called the probability mass function. So what do I get? If I summed up, and usually it's small probability mass function of the possible outcomes, which I'll call x. From x equal 1 to 6. But does that have to be? It's obvious. 1. Has to be 1. The likelihood that any possible outcome happens has to be 1. That has to be 1. Now, anytime you talk about the probability mass distribution, they're discrete values. What's the probability, just probability, of, and here's how I'm going to do it, the probability of the outcome, we're going to call x the outcome. It's just the value of the roll. The outcome, x, and usually they do it with a capital X, and it just means that that is a random value. This is a discrete random variable. Between, I'm using an equal sign here, between 2 and 5. Now, mathematically speaking, what I would do is say, this would be the summation, and here it would be from x equals 2 to x equal 5 of the probability mass function of x. Does this make sense to you? And I'm saying I'm using greater than or equals. If I use a greater than sign, then 2 wouldn't work. Here's the lower limit. Do y'all follow me? So that's, he makes a distinction that I will use greater than or equal signs, or just greater than or less than signs. But I'm not going to use his nomenclature the way he does this, because I think it'll confuse you. This is the way you see it in engineering. What's that going to be? Well, it's probability of 2, probability of 3, probability of 4, probability of 5. Agreed? There are 4 possible outcomes involved, right? The total number is 6. You all see that's 4/6 or 2/3. How many understand that idea? So that's probability mass function. It shouldn't be hard. He'll do this axiom stuff, and he'll talk about how it can't be negative. Anytime you have an event, you can't have a negative outcome. You can't have the probability is minus 0.5%. It makes no sense. It's an undefined idea. It really is. So it has to be a positive. The probability and probability density, the probability mass function, have to be strict positives. The sum of all possible, the probability of all possible outcomes has to be 1. And that really is it in a nutshell. We could talk about what it means to be independent and all that, but we just did with the Venn diagram, so that should be clear to you. With me? Okay? Now, he has a lot of examples of probability. He has some Python code. How many know Python in here? 1 or 2. How many know MATLAB? Everybody's supposed to know MATLAB in here. No? A little bit. well, I'm not gonna force you to do MATLAB to hand it in, but some of this stuff is very useful to to play with for one reason. I mean, you can think, well, I don't need it. Well, it's true, you don't need it to pass the course, but it'll help a great deal. It'll help you down the road. Python, I'm learning. I hate downloading all those. Every time I want a simple function in MATLAB, I have to download all these other things, which irritates me, but I guess you could have one code that does it all in the beginning and just work with it. And he's going to talk about histograms. So basically, you see this right here? Say we had a die, we didn't know the probability mass function was that, but I had a die. Now, obviously, we don't know if it's loaded or not. Basically, we don't know if there's a weight to favor one side to me. If I threw that thing about 1 billion times, and I looked at how many times a 6 came up versus a 5, if it was a fair die, that's what you'd get. So that's called a histogram of the events. Are you familiar with that term, histogram? It means from the history of all events, that's what the result is for the probability mass function. And don't get hung up in the verbiage there, because it doesn't do anything. Well, he has a probability mass function versus histogram. Probability mass function is something that is assumed absolutely true. The histogram says for the number of times we've done this, this is what we get. But usually in the limit, the two are 1. Okay, then he talks about a cumulative distribution function. And all that is now if you want the probability of something occurring, you just sum up the probability mass functions that have those values. Do y'all follow me on that? Just like I did with the die. That's all he's saying in part that. I'm going to get this stuff moving. Now we're going to get the expected value. So, stick with this one and you'll see what I'm getting at. When you, have you heard the term expected value? Or no? If I say that, you know what roulette is? Do you know what roulette is? It's the thing where you throw a marble, basically. You let the thing spin and go in it. Well, is it 36 spots on a roulette wheel? I forgot how many. All right, so what they do is a little trick. If you get the right, if you guess, say 18, and the marble falls on 18, you're paid out of value, but it's not 36 over 36 times the original one. It's 35 over 36. So if you put $50 down, you're going to get 35 out of 36. Or basically, sorry, it'll pay out 35 times as much, not 36. What that means is the house always wins. If you got a large number of people playing, they never pay out what they take in. They always keep that 1 out of 36 for every dollar spent to themselves. You all with me? The expected outcome for your money spent on that, if it's random, is negative. You're going to keep losing money. That's an expected outcome. I'm trying to just give you an idea of something I didn't know. Now, when I talk about the expected outcome of rolling a die between 1 and 6, what I'm really talking about is what value do you expect to, what do you think is the most common value that you're going to get? Here's how you get it. You'll see it. The expected outcome of rolling, you want to know the expected outcome of rolling a die, is really just going to be equal to the sum. This is of x. This is going to be just for the die. It's going to be the sum, and here it would be from I equals 1 to 6 of the probability, or really the value x. And that's going to be 1, 2, 3, you all with me? And then it's going to be times the probability of x. So I want you to think about what I just did. This is the expected outcome. Does it have to be an integer? No, not necessarily, which is an impossible value. But this would be the expected value. If you're rolling a dice over and over again, you with me? What is that going to be? Now think about it. Would you all agree that P of X is 1/6 for every single one of those? The probability of rolling any value is 1/6, right? We can take that out front here. And now, what am I doing? I'm summing the numbers, really summing X. I'm gonna put X equals 1/6. I'm gonna sum the numbers, and here it's gonna be X equals 1/6 of X. So I have 1/6, and then it's gonna be 1 plus 2 plus 3 plus 4 plus 5 plus 6. And that's gonna be, if you look at this, I got 3 and 3, 6 and 4 is 10, and 5 is 15, and 6 is 21, so it's 21/6. That would be the expected outcome from rolling a die. It should bother you. Is there a 21/6 outcome? But that is what's called the expected value. It doesn't mean it's possible, it's the most likely value in theory. You all with me on this? That's the expected value. Where this is really useful is in continuous. When you have continuous probability mass functions, they're called probability distribution functions. I'm over by 1 minute. I'm going to give you some of these problems. I'm going to give you a couple more, the joint, disjoints, some other things. I'm going to put up, now listen, I'm going to put up problems that aren't in the book, but I will provide you with the answers or solutions or both, and I want you to do them. Friday is coming up quick. Friday, we should have a logical question or a quiz. Make sense? Yes. All right. What is the quiz going to be regarding? It'll be regarding the homework from last time and this. Specifically, from chapter 2, it would be independent or non-independent, like I did, and it will also be on the basic probability math stuff. That way I can be sure you do it. It won't be hard. I mean, that to me looks obvious. But if you do the homework, you should have a very clear idea of what's coming. The last quiz I thought was very fair, and you did a good, overall very good job. Some silly mistakes. Now you'll notice I telegraphed that one. I will telegraph this one too. Make sure you do the homework.